Welcome everybody. Today we will be solving a problem that I usually ask my students in my pre-calculus. So in solving this problem, we are not allowed to use any calculus or any advanced mathematics, or we are not allowed to use any computers. So you're going to be using as little knowledge as possible, and we will see that it's possible to solve this problem just using pre-calculus knowledge. So the question says, are there any real roots of this polynomial, x to the fourth plus x cubed plus x squared plus x plus 1? So as you know, polynomials are continuous functions. And when do we have real roots? So let's go over that a little bit. So when we have a continuous function, we may have a real root when the function changes sign, right? From positive to negative. So here we go. So we have a real root here. So by the way, this is my y-axis, x-axis. So the second case, the function may go from negative to positive, right? So we also have a real root here. So it's y and x. There are two other cases. One, the function may be tangent, right, to the x-axis. So we have a real root here. Or the function may be tangent from this direction, right? So we also have a real root. Suppose these are two different functions, of course. And when do we have no roots, or in other words, no real roots? A function may be all positive, or it may be all negative, right? So it doesn't cross the horizontal line, so there's no any intersection on the x-axis. So in these two cases, there are no real roots. Okay, so our first observation here, so since the coefficients of these terms are all positive, so the first case, when x is larger than 0, right? So p of x is always larger than 0. So it looks like this case here. So you'll have no real roots in this domain. So when x is equal to 0, it's equal to 1. So I can actually include x is equal to 0 in this case. The second case, so I don't want to go too far from x is equal to 0. I have already excluded half of the real axis, right? So I'm going to make a smart choice here. So I'm going to say, let's say x is less than minus 1. So when x is less than minus 1, what we can observe here is we can actually pick some numbers like minus 2, minus 3, minus 4, minus 5, and you can actually check this argument here. So x to the 4 absolute value is always larger than the absolute value of x cubed, right? I'm comparing these two terms, but they're absolute values. So as you know, in this domain, this term is positive, this is negative. But when I compare the magnitudes, x to the fourth is larger than x cubed. So since x is less than minus 1, this becomes x to the fourth is larger than minus x cubed, because x cubed is always negative, right? So this actually tells me that x to the fourth plus x cubed is larger than 0. So similarly, I'm going to compare these two terms. So x squared is larger than x. So x squared is larger than minus x. So x squared plus x is larger than 0. So what do I see here? I have these two results. So this term plus this term plus this term plus this term. So the sum of these two inequalities. So they're all larger than 0. The sum is larger than 0. Plus 1 is even larger than 0. So when x is equal to minus 1, this is 1, minus 1, 0. 1, minus 1, 0, is plus 1. So it's also positive. So this polynomial is actually positive when x is less than or equal to minus 1. So again, similarly, so we can say there are no real roots in this region. So I think the idea is clear now. The third region that we need to look at is now x less than 0 and x larger than -1. So if there are any real roots, okay, they have to be in this interval. There is no other case, right? We have already excluded these two. Okay, so for this, I'm going to write this polynomial in a little bit different way. So I'm going to take this term and the third term. So x squared, I can use the x squared parentheses. So this gives me x squared plus 1 plus. So I'm going to combine the second and the fourth terms. The x parentheses, it's going to be x squared plus 1, right? And then we have plus 1. And I can erase this. We have already understood this part. So I'm just going to erase that. Okay, so I can combine these two terms now. So they both have x squared plus 1. So x squared plus 1 parentheses, I have x squared plus x, then plus 1. Okay, so if I look at this function here, x squared plus 1, this is always larger than 0 in this interval, right? So this is always larger than 0. And it actually, I can actually put an upper bound to that. So x squared can get 1 at most, right, in that region. So x squared plus 1 is always less than 2. Okay? When x gets close to 0, well, it gets close to 1, right? X squared plus 1 gets close to 1. So x squared plus 1 is always positive, and it takes values in between 1 and 2. Okay. So this is positive. 1 is positive. So I'm going to create some negative numbers, right? Because this polynomial is also positive in these two domains. So can it ever get any negative values, right? This is what I'm trying to find. So the only possibility is when this function is negative, right? I may get some negative values for p of x. So let's plot this x squared plus x. So I'll call this function f of x. Now, what is f of x? X squared plus x, right? So I can put it in this way. So x times x plus 1. Well, this is nothing but a polynomial, right? Actually a parabola. And its roots are 0 and -1. Wow, this is interesting. -1 and 0. -1 and 0, right? So when I plot it, so it's going to be an upward opening parabola, right? This is y, this is x-axis. So this is -1 and 0. Well, it takes negative values. This is good, right? I want to get negative values. So the minimum that it can get is going to be at its vertex, right? The vertex is going to be at the midpoint. This is the property of a parabola, right? Opening upward. So the vertex is going to be at x is equal to -1/2. It's the midpoint between these two roots. So when I put -1/2 here, the minimum value turns out to be -1/4. So I'm going to create really large negative values, right? So the minimum of this is actually -1/4, right? And this term can get at most 2 or close to 2, values close to 2. So I can actually put a lower bound for my function p of x. So let's see what it is. So p of x can get values larger than, so I'm going to create as large negative value as possible here. So 2 times -1/4 is -1/2. Then plus 1, I have plus 1 here. So this is equal to 1/2. Wow, this is something really interesting, because this result tells me that whatever my x value here is, in between -1 and 0, this polynomial can never get values less than 1/2. Okay, so this 1/2 is not the minimum value for p of x. It's just a lower bound. So whatever the minimum value of this p of x is, it has to be larger than 1/2, which is larger than 0. So this tells me that this function polynomial, this polynomial function can never get any negative values. Okay, so this region is also gone. So the answer to this problem, this question is, are there any real roots of this polynomial? Simply no. Okay, so does this mean it doesn't have any roots? No. It may have complex roots, but it's not the topic that we want to discuss today. So I hope you enjoyed this problem. So as you see, we didn't use any calculus, any advanced math, or we didn't plot this function. But as a homework problem to you, I want you to plot this function using a graphing calculator and try to figure out the minimum and maximum values of this function. And I also want you to see that this function never gets any negative values. So this is all for today. I hope you enjoyed it. I'll look forward to seeing you next time in different problems. See you later, guys. Bye.